All right, so we're diving into some pretty fascinating stuff today.
Yeah, this is going to be fun.
We've got what looks like a whole treasure trove of info here.
It does, doesn't it?
Looks like official study material for this exam, the H35 580 V2.0 ENU. Now, we're not actually prepping for a test or anything.
No.
But this document is like a backstage pass to the world of cutting-edge mobile network tech.
Absolutely.
Specifically 5G.
Right.
So we've got the exam basics, the format. It's a mix of multiple choice, single choice, true, false.
Yep.
90 minutes to sweat it out. Passing score is 600 out of 1,000.
Oof. That's a lot of points.
$200 to take in. You can choose between Chinese and English.
Interesting.
But the real gems here are the practice questions.
Oh, those are gold.
We're going to look at 10 of these.
Sounds good.
Each one's like a little key.
Okay.
Unlocking some core concept about how these modern mobile networks actually work.
Like a cheat sheet.
Exactly. You get to grasp these essential 5G ideas without the pressure of an exam.
Much better.
So no stress, just pure learning.
I like it.
What really jumps out at me is the sheer depth of knowledge here.
Oh, yeah. It's impressive.
I mean, these questions touch on some really intricate stuff.
They do.
About how these next-generation networks are designed, deployed, optimized.
It really shows you the complexity of it all.
Doesn't it?
It does.
It's a testament to how far mobile technology has come.
Absolutely.
Okay, so let's jump right in.
Let's do it.
First question.
Okay.
It's all about continuous carrier aggregation
Interesting.
in the N41 band. Now, carrier aggregation, as you probably know,
Right.
it's this idea of combining different radio frequencies.
Like adding lanes to a highway.
Exactly, to give you those super fast data speeds.
Makes sense.
This question specifically asks about the maximum spacing allowed
Okay.
between a 40 megahertz carrier and a 100 millihertz carrier
All right.
within that N41 band.
Got it.
The answer, 79.8 megahertz.
Very specific.
Right, it seems super precise.
It does.
But it's not just some random number.
I'm sure it's not.
It's crucial for making sure those different radio signals can work together smoothly.
Without interfering.
Right, without stepping on each other's toes, so to speak.
Yeah, like a delicate balance.
Exactly. What's the key takeaway here?
Well, this 79.8 megahertz isn't arbitrary at all.
Okay.
It's actually a carefully engineered spec determined by organizations like 3GPP.
Right. 3GPP.
Which sets those global standards for mobile communication. This specific spacing in continuous carrier aggregation for the N41 band, it ensures enough frequency separation.
So they don't interfere.
Exactly.
But they're still close enough to be combined.
Right, for higher bandwidth and better data throughput.
That's the key.
Yeah, the practice question even mentions it.
Oh, yeah.
Proper signal overlap and resource scheduling.
Right.
This spacing makes all of that possible.
So it's not just throwing frequencies together. It's a very deliberate process.
Very much so.
To make sure they all play nicely together.
Harmony in the radio waves.
Love that. All right, question 2.
Bring it on.
This one shifts gears a bit.
Okay.
From the waves themselves to the actual rollout of 5G.
Interesting.
It asks which company first completed standalone networking function verification?
Standalone.
Okay.
That's the key word here.
Obviously.
For the domestic IMT 2020 5G promotion group. And the answer is Huawei.
Interesting.
Now, we've all heard about early 5G being rolled out on top of existing 4G infrastructure.
Yeah, piggybacking on the old stuff.
Exactly what makes standalone so different.
Well, that's a huge distinction.
It is.
Early 5G, what we often call non-standalone.
NSA.
Yeah, NSA.
Okay.
It used the control signaling of existing 4G LTE networks.
It was kind of a hybrid.
It was a way to boost speeds initially.
A stepping stone.
Exactly.
But standalone 5G.
That's the real deal.
That's
SA.
right.
Yep, a complete paradigm shift.
Wow.
It's about deploying a brand new 5G core network.
From the ground up. Totally independent architecture.
That's incredible.
It unlocks the full potential of 5G.
The things we've been hearing about.
Ultra-low latency network slicing.
Right, network slicing.
The ability to create virtualized independent network partitions.
Wow, so different services can have their own dedicated slices.
That's the idea.
That's amazing.
Huawei achieving this verification.
Under China's IMT 2020 5G promotion group.
Yep, it signifies a major step.
A big one.
Towards 5G maturity and readiness.
For real-world use.
For widespread deployment.
Independent of the old tech.
Completely.
It's like going from training wheels to a brand new bike.
A perfect analogy.
Okay, question 3.
Hemi.
This one takes us into the world of keeping these networks running smoothly.
Sounds important.
It's about automatic neighbor removal, or ANR.
ANR. Okay.
The question asks what factor is not considered
All right.
when the network automatically decides to remove neighboring cells. The answer they give is the presence of the X2 interface configuration.
X2 interface, all right.
Now, for those of us who aren't network engineers,
Right.
how can we understand what ANR does?
Sure.
And why that X2 interface isn't a deal breaker for removing a neighbor?
Okay, so think of ANR like a smart traffic management system.
For cell towers.
Exactly. It's constantly optimizing the relationships between those towers.
To make sure our phones hand off smoothly.
Exactly, as you move around.
It's working behind the scenes.
All the time.
To give us that seamless experience.
Right.
So ANR is evaluating potential neighbor cells based on a bunch of performance metrics.
Like what?
Things like how often a particular neighbor is actually used.
For successful handovers.
Right. If its configuration aligns with the current cell.
Makes sense.
And if it follows the network's predefined rules.
Okay.
Now, the X2 interface, that's a direct line of communication.
Between base stations.
Technically, ENBs and 4G, GMBs and 5G.
Right, the technical terms.
Having that X2 interface, it can definitely speed up handovers.
Between those specific neighbors.
Right, but just because they can talk quickly.
Doesn't mean they should be best buddies.
Exactly. It's more about the quality of that connection.
And its relevance to overall network performance.
It's about picking the right neighbors, not just the fast talkers.
Exactly.
That makes a lot of sense. Okay, question 4.
Okay.
We're zooming in on your phone now.
Interesting.
Specifically, SRS transmission.
SRS.
Sounding reference signal.
Okay, got it.
The question asks which parameter tells us if a device supports antenna switching during this process. And the answer is pretty straightforward.
Let's hear it.
Supported SRS antenna switching.
Okay, makes sense.
It's a mouthful.
It is.
But what's the real benefit?
Yeah, why do we care if our phone can switch antennas during SRS?
Well, this is where it gets cool.
I'm intrigued.
Your phone is actually helping the network.
How so?
By giving it a better understanding of the radio environment.
Interesting.
The sounding reference signal is like a signal your phone sends out. So the base station can figure out the quality of the uplink channel.
The path from the phone to the tower.
Exactly.
Got it.
Now, if your phone can switch antennas during these signals, it's basically giving the network multiple views.
Multiple perspectives.
Yeah, of the radio conditions from different spots.
So a more complete picture.
Exactly, and that allows the network to get really smart.
In what way?
It can use techniques like uplink beamforming.
Beamforming, I've heard of that.
It's like focusing the radio signal directly towards your device.
So it's a more targeted connection.
You're right, leading to better uplink performance.
Especially in tricky situations.
Yeah, like weak signal areas or crowded places.
Makes sense.
So your phone's basically giving the cell tower a map.
A radio map.
Yeah, so the tower knows exactly where to listen.
To get the best connection.
It's amazing how they work together.
It is pretty amazing.
Okay, question 5 brings in a familiar term.
Okay.
MIMO.
MIMO. Multiple input, multiple output.
That's the one.
I've seen that before.
This question focuses on the acceptable deviation in RSRP.
Reference signal received power.
You got it.
Okay.
Across multiple receiving antennas for optimal MIMO performance.
So how much difference in signal strength can we tolerate?
Exactly, and the answer is 6 dB.
6 dB. Okay.
Why is staying within that range so important?
Well, MIMO is all about boosting data speeds and capacity.
It's a core technology.
It uses multiple antennas.
At both ends.
The base station and your phone.
Right. To send and receive multiple data streams.
Simultaneously.
Over the same frequencies.
It's like having parallel data pipes.
Exactly, instead of just one.
Much faster.
But here's the thing.
Yeah.
For MIMO to work its magic,
right,
the signal strength on each antenna needs to be fairly balanced.
Okay.
If that RSRP deviation goes beyond 6 dB, it means some antennas are getting a much weaker signal.
Right, so it's uneven.
Exactly, and that makes it hard for your phone to decode those data streams.
Like trying to listen to multiple conversations at once?
Yeah, and some are really quiet.
You miss parts of it.
You lose the benefit of MIMO.
The speed advantage goes away.
Keeping that balance within 6 dB?
Ensures everything's running smoothly.
Make sure you get those fast, reliable data connections.
And a better overall mobile experience.
Exactly. Question 6.
Right.
This one's about the very first moments when your phone connects to a cell tower.
That initial handshake.
Exactly. It's called the random access process.
Interesting.
The question asks which message provides the timing info.
Timing is crucial.
It is.
Especially at the beginning.
During this initial handshake.
Oh, wait.
And the answer is the random access response.
RAR.
RIR, yep.
All right.
Why is getting the timing right so essential?
Well, imagine a room full of people all trying to talk at the same time.
Chaos.
Total chaos. You can't understand anything.
It'd be a mess.
Same thing with wireless communication.
Right.
Your phone needs to transmit its messages
At the right time.
at a very precise moment.
So it doesn't clash with other devices.
Trying to do the same thing.
Like a perfectly choreographed dance.
In a way, yes.
The random access response.
Right.
It comes back from the base station, and it contains those crucial timing commands.
So the phone knows when to talk?
Exactly. It tells the phone to adjust its clock.
Synchronize?
And make sure its transmissions arrive at the right moment.
At the base station.
Right. Without that,
You get collisions.
the connection fails.
It's like a train wreck.
So that timing is everything.
Absolutely fundamental.
Question 7 takes us down to the nitty-gritty.
Okay, ready.
The structure of the radio signals themselves.
Deep dive.
It's about subcarrier spacing and time slots.
Right.
The question asks, how many time slots are in a 10 millisecond radio frame?
10 milliseconds. Wow.
When using a 60 kilohertz subcarrier spacing,
60 kilohertz. Okay.
the answer is 40.
40 time slots.
And each slot is a tiny 0.25 milliseconds long.
That's incredibly short.
It's mind-boggling, isn't it?
It is.
This level of precision in 5G is just incredible.
It really highlights the precision of 5G new radio.
5G-NR.
Yep.
That's subcarrier spacing.
Right.
It determines the frequency separation between subcarriers.
Which make up the radio channel.
Exactly, and a larger spacing like 60 kilohertz.
Leads to shorter time slots.
And why do we want those shorter slots?
Because they're crucial for low latency applications.
Things like autonomous vehicles.
Right.
Industrial automation, real-time gaming.
Where every millisecond counts.
Absolutely. That 10 millisecond radio frame, it's a fundamental unit in both 4G LTE and 5G NR.
Right. It carried over.
And the number of time slots inside depends on that subcarrier spacing.
Okay.
So 5G can adapt
by changing that spacing
to meet the needs of different services.
Some need more speed. Some need lower latency.
It's all about flexibility.
It's a brilliant design.
Think of these time slots like tiny little containers.
For information.
And the subcarrier spacing determines how many fit in that time frame.
Like packing a suitcase?
Exactly, except we're packing milliseconds with data.
Amazing.
Question 8 dives into resource allocation.
Resource allocation.
How the network divides its radio frequencies among users.
Like slicing up a pie.
And making sure everyone gets a piece.
Right.
It focuses on type 0 resource allocation.
Type 0.
For a 100 megahertz 5G NR cell, using this type, the smallest unit of frequency you can schedule is 16 resource blocks.
16 RBs.
Why that specific number?
In Type 8, the bandwidth is divided into these groups of resource blocks called resource block groups, or RBGs.
Okay.
And for a 100 megahertz cell, each RBG is set to 16 RBs.
That's the sweet spot.
It's about finding a good balance.
Between what?
Flexibility and overhead.
Okay.
The network needs to be able to allocate resources to users.
Right.
But it also needs to communicate those allocations efficiently.
So not too much back and forth.
Exactly, by grouping resources into these bigger blocks.
Makes it easier to manage.
It reduces the control information that needs to be sent.
So less chatter, more action.
Basically, it's about making sure no one hogs the bandwidth.
And everyone gets a fair share.
Exactly. Optimizing capacity and performance.
So it's like having the right size plates at a buffet.
You serve everyone properly.
Without creating a huge mess.
I like that analogy.
Question 9. We're going even deeper into those signals from the tower.
Okay.
It asks about the size of the PBCH payload.
Physical broadcast channel.
Yep. Within the SSB.
Synchronization signal block.
You got it.
Right.
When 20 resource blocks are being used, the answer is 864 bits.
864 bits for the payload.
What's packed into those bits?
Well, that payload,
Yeah.
It's like the cell tower's welcome message.
Essential info.
It contains the master information block, the MIB.
Okay.
It gives your phone the basic parameters
To connect.
to perform those initial access procedures.
Right.
Things like the system frame number, the cell ID.
So the phone knows where it is.
And how to talk to the network.
It's like the network's ID card.
In a way, yes.
The SSB.
The synchronization signal block.
It includes that PBCH.
Along with other
Their
signals.
PSS and the SSS.
Primary and secondary synchronization signals.
Those are for getting the phone in sync with the cell.
In time and frequency.
Right. Then the PBCH provides that essential system info.
To actually establish the connection.
It's a multi-step process.
Very carefully defined.
To make sure it's robust and efficient.
Yeah, every bit counts.
Absolutely. Okay, last question.
Bring it on.
Back to carrier aggregation.
Okay.
But this time we're looking at when the network might say goodbye.
To one of those aggregated carriers.
Right. The secondary cell or cell.
Got it.
The question asks which metric is not typically used
for making that decision.
To deactivate a carrier?
Okay.
And the answer is the SRS-based spectral efficiency report.
SRS, again, interesting.
Why wouldn't the network use that report?
Remember, SRS is mainly about the uplink.
From the phone to the tower.
Exactly. It helps the network schedule uplink transmissions.
And manage power.
But deciding to deactivate a downlink carrier,
the cell,
is about optimizing the downlink data.
From the tower to the phone.
And conserving resources.
Both network resources and your phone's battery.
Right. So the network focuses on metrics that directly show
downlink demand and efficiency.
Exactly.
Like
things like the UE uplink buffer report.
Which tells the network how much data your phone needs to send.
If it's not sending much.
Maybe it doesn't need that extra carrier.
Exactly. It also looks at the downlink throughput on the cell.
If it's not being used much.
Time to shut it down.
And importantly,
the CQI-based spectral efficiency.
Which estimates how efficiently data can be transmitted.
On that specific carrier.
So the network is constantly analyzing.
Making adjustments.
To make sure those extra lanes are only open.
When they're actually needed.
It's all about optimization.
Smart network management.
What other questions do you have now?
What else do you want to explore?
Keep digging, keep learning.
The world of mobile tech is vast.
And constantly evolving.
There's always something new to discover.
So go out there and find it.
Happy exploring.
Exactly. And until next time, stay curious.
Keep those questions coming.
And keep that signal strong.
And that battery charged.
We'll see you on the next deep dive.
Looking forward to it.